We've said that bonds should be formed by the overlap of orbitals from the atoms being bound together. Okay. One thing we haven't done yet is we haven't reconciled that idea with how we can make a double bond, for example. Right. We've drawn a lot of structures where we have double bonds or triple bonds, multiple pairs of electrons being shared between the same two atoms. We haven't yet looked at any idea of how to explain how that happens. All right. So let's do that now. Molecule I'm going to work with is ethylene, which is C2H4. It's a multi-center molecule as well, meaning it doesn't have just one central atom. It's got, in this case, the two carbons, right? But let's try and describe that using our steric number model, looking at the two carbons both as being central atoms, okay? Each carbon, if I look at the carbon there, say, it's attached to three atoms. And it's got no lone pairs. Right, so that means it gets steric number of 3, like it says up here, which means we want each of the carbon atoms, they both look the same, so they should both have sp2 hybrid orbitals, okay? Remember, those are the ones that are in the trigonal planar arrangement, right? So they point at 120-degree angles with respect to one another like that. And you'll notice that the shape, I've drawn the Lewis structure in here, kind of matches that, right? So I've got my 120-degree angles here and there. In this case, the program I use to draw those just kind of automatically does that, to be honest. But then I have to figure out how to make the remaining bond. Okay, so they're sp2 hybrid orbitals. That means from the carbon atoms, we use the 2s orbital and 2 of the 2p orbitals, right? Because that's what the superscript 2 on sp2 means. I use 2 of those to make the hybrids. That means, so the first bond in there is going to be an sp2 hybrid from this carbon overlapping with an sp2 hybrid from that carbon. The second bond is going to have to come from, it turns out, the remaining p orbital, right? Because when I mix together the s and 2 of the p's, I left a third p orbital that is not yet used, okay? And that's how we're going to end up making that, that double bond. That third p orbital is going to be the one that's perpendicular to the plane that the hybrid orbitals are in, right? So if all these orbitals are like I drew here in the plane of the screen, then the last orbital, the p orbital that's not part of the hybrids, is going to be sticking in and out of the screen. Okay, so you can imagine it being just perpendicular to the plane of the screen you're looking at, and that's where those p orbitals are. Okay, so how are they going to make the bond? All right. Essentially, if I were to take and imagine the molecule being flat, like the atoms all being in this plane here. Okay, right now I know that the two hydrogens on the carbon and the carbons, those atoms are all in one plane. I don't yet know how the two planes relate to one another, right? But if I get them so that they're both the same plane, they're coplanar, then I'll have a p orbital sticking up vertically, say in this direction, another one here, right? In the picture coming out on the screen, that would be in and out of the screen, right? If I do this, then as these atoms get pulled together, these orbitals are going to be able to overlap side to side. Because remember, those p orbitals, they have that dumbbell shape to them, right? So they've got some width, essentially, okay? And so it's the overlap of those orbitals that are going to make the second bond. We call this bond a pi bond for reasons that I will explain momentarily. The normal bond, the single bond, the first bond of the double bond, is called a sigma bond. Okay, and I'll talk about that some more in the video here as well. Let's try and take a look at what the orbitals would look like for this. Okay, I've got a figure here which is maybe not the best, but it's better than I can sketch. So here we've got the way our C2H4 molecule would look. And let's look on the left-hand version, the A panel of the figure, okay? So this is nucleus of one carbon atom. This is nucleus of the other carbon atom, okay? The yellow orbitals there represent the set of sp2 hybrids. So each one of those yellow lobes is one orbital. That's the part where this figure is a little confusing, is that the yellow lobes are one orbital. The blue circles on the ends of those are the 1s orbitals from the hydrogen atoms, right? And so those overlap with the hybrid orbitals to make the single bonds, which we're now going to call sigma bonds, lowercase sigma, that's this symbol here, okay? And then I have the p orbital, right? So all of those are in a plane. The two carbon atoms and the 4 hydrogens are all in the same plane. That's what's indicated by the blue rectangle there. That's trying to map out that plane. Then I've got the p orbitals that are not in the hybrids. Those are represented here, where this blue and red lobe there, those are both lobes of the same p orbital, right? Again, the blue and red represents different signs of the wave function, a sort of subtle point. This one likewise. If they get like this, and if you imagine those atoms being pulled closer together, what would happen is that those orbitals would be able to overlap, not end to end like we've been picturing, but now side to side. Okay, that sideways overlap makes what we call a pi bond. Okay, one way to sort of distinguish the sigma bond and the pi bond is if you could look along the line connecting the two atoms, a sigma bond has the electron density on that line. Like this bond here, if I could look down like sight along here, so I'm looking through both of the carbons, right? The electrons that are in that bond, they'd be centered on that line. The electrons that are in this pi bond, they would in fact be above and below the line. If I again looked down the line here in the plane, right, I wouldn't be able to see the electron cloud that's in the pi bond because it would be above and below the line I'm looking at. That's what it means to be a pi bond. Okay, there's a simpler way to describe that, which I'll do after we look at one more example. I'll give you another way just to count those up, which is a lot simpler than thinking about how they look that way. Okay, so that's how we make a double bond, we just take other orbitals that are available, in this case the unhybridized p orbitals, and we let those overlap. I could do the same thing. If I wanted to make a triple bond, basically I just have to do that same thing only twice. So the simplest carbon-based molecule with a triple bond in it would be acetylene, that's C2H2. So my two carbon atoms now have a triple bond between them, right? Carbon atoms are attached to two other atoms, a hydrogen and the other carbon. That means they have steric number 2, which means they get sp hybrid orbitals. Sp hybrid orbitals point 180 degrees apart from each other, right? So they're in a linear arrangement. That means this whole molecule is going to be linear, right? All 4 atoms are on a line. When I make the sp hybrid orbitals, I'm using the 2s orbital from carbon, and I'm also using one of the 2p orbitals. So now I have a pair of 2p orbitals left on each carbon. Those other 2p orbitals are perpendicular both to each other and to the line that the hybrids are on, okay? And so that's going to let me make 2 pi bonds, because now I'm going to be able to do this sideways overlap twice. If I have one pair that would be like this, then the other pair would be sort of in and out this way. It's a little hard to do that on the little screen there. I'd get a pair of those things, one going this way and one going that way. I guess it's easier if I do fingers instead of arms. And again, both of those pi bonds are made with the sideways overlapping of things. So if I call the axis of the molecule the z direction, then I make my pi bonds out of the px and the py orbitals from each of the atoms, okay? I think I have the same sort of figure with the orbitals here as well, okay? So now, again, the yellow lobes, each one of those yellow lobes represents an sp hybrid orbital, okay? And then I've got the s orbitals from the hydrogens on the ends of those. The p orbitals, the unhybridized p orbitals, are still drawn the same way. So a red one and a blue one, the red one and the opposite blue one represent a single p orbital, right? Because the p orbital, remember, exists on both sides of the nucleus. So now I have a sigma bond, which is the yellow electron cloud, which is on the line of centers, right? Then I have a pair of pi bonds. I have one of them that is, in this case, above and below the line, and one that is, say, in front and in back of it with respect to the screen. All told, that gives me my triple bond, okay? So in my triple bond, I have one sigma bond, and I have 2 pi bonds, okay? And then the single bonds that just go to the hydrogens are also sigma bonds, if we want to count them up that way. So that's how we can envision making multiple bonds. In class, probably I'll talk a little bit about how this same idea can be used to explain what really is happening when we look at molecules where we draw resonance structures as well. So I promised you a way to just count these things up, okay? And here it is. If I talk about things in terms of this, picturing the bonds from overlap of orbitals and labeling them as sigma and pi bonds based on the arrangement of the overlap, right? Sigma is sort of end to end and pi is sideways, right? S orbitals can only make sigma bonds because if you're a sphere, there's no such thing as sideways, right? Every direction is the same. If I have a double bond, a single bond is always just a sigma bond, right? So the first bond between a pair of atoms we can think of as being a sigma bond. Double bond is 1 sigma and 1 pi. A triple bond is 1 sigma and 2 pi's. So again, you can always just say the first bond is a sigma and the additional bonds are pi's, and that will work, right? If you're just asked to count up how many of each type, that's the simplest way to do it, is just say in between each pair of atoms, I get 1 sigma bond and any other bonds that are in there are pi's. The last thing I want to do in this video to finish up is to take a look at what happens if we want to consider a larger molecule. Okay, we've done Lewis structures off and on for a while now. We've drawn structures for a lot of small molecules, things that just have one central atom. Okay, most of the interesting molecules in the world, frankly, are bigger than that. They don't just have a single central atom, and obviously we want to be able to describe those as well. So if we want to do this, what we're going to do is have to do it piecewise, right? We essentially just go down the chain or the backbone of the molecule, and we consider the central atoms in turn. Any central atom is one member that's bound to more than one other atom, right? I figure out the geometry around each one of those, and then I can just sort of imagine or visualize how they would piece themselves together. So I'm going to just do an example of that for us here to wrap up this segment. So this molecule its name is peroxyacetyl nitrate. It's involved in urban smog, among other things, right? I've drawn out a skeleton for it because the first step in our Lewis structure algorithm, remember, is that we have to count up the electrons, but then we have to get a skeleton structure. We have to know what atoms are connected to each other, okay? So if I just gave us the atom count, we would not be able to come up with this as the particular arrangement of atoms we wanted, right? So we need to know that. What am I going to do? I'm going to finish the Lewis structure. I'm going to figure out what the hybridization should be for all of the inner or central atoms. And then I'm going to look at what I think the bond angles should be around those central atoms as well, and try and envision what the molecule as a whole might look like, okay? I want some more room to write, so I'm just going to go to a slide that just has nothing on it but the molecule itself, okay? So let's see, I'm going to need the electron count, okay? So let's do that. It's a little bit more work than usual. The carbons, I have 2 carbons. Each carbon has 4 valence electrons, so that's 8. I have nitrogen. I have 1 nitrogen, and nitrogen has 5 valence electrons, so that's 5. Oxygens, I have 1, 2, 3, 4, 5 of those, and oxygen has 6 valence electrons, so that's 30 more. Hydrogens, I have 1, 2, 3 of those. Each one has 1 valence electron, so that's 3 additional electrons. Put all that together, and it looks like I have 46 electrons to work with, okay? Obviously, that's more electrons than we usually have had. My procedure for drawing Lewis structures, digging back a ways, is what? I want to start off with those electrons by just counting up how many are in the bonds, right? Right now, I've got, let's see, let's try this thing just for fun. Right now, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 bonds drawn in my molecule. And so that tells me that each one uses 2 electrons. So I've got 20 electrons in the bond. So I've got 26 more to go. Next up, I want to sprinkle electrons around the outer atoms. My outer atoms in this case, I can't do the hydrogens, but I have 3 oxygens there that are not attached to anything but 1 atom, right? So they each get 6 electrons. That's my next move, is to put 3 lone pairs around each of those 3 oxygens, since I have plenty of electrons, it seems like, to do that, okay? So that was 18 more, so I still have 8 to go. Next, I want to put those 8 electrons somewhere, okay? The places where I could put them are anywhere in here, right? Those are the atoms that do not yet have octets, my carbon, the 2 center oxygens, and the nitrogen, okay? I have 8 electrons. I'm going to take them and I'm going to put them on the oxygens. I'm going to do that largely because oxygen has the biggest electronegativity out of those 3 elements that are in there, so that means it's the one that wants electrons more. That's more likely to get them in the right place or close to the right place than if I put them somewhere else, okay? If I put them somewhere else, I just have more work to do to clean up my structure. At this point, I've got all the electrons in my structure, so I can stop with the count over there, all right? Now I have to evaluate my structure, and if you look at that structure, you should see pretty quickly 2 places that should strike you as needing work, okay? That's this carbon and that nitrogen, because neither one of those currently follows the octet rule, all right? And so that's where I have to get something done, because I have to obey the octet rule for this. So we know from past experience what this means. It means we're going to have to make a double bond to each of those. In both cases, we've got some choices, right? Let's start with the carbon. We've got a choice of either taking a pair of electrons from the oxygen on the top there, or taking a pair of electrons from the oxygen that's in the center of the molecule, okay? Probably the best way to do this is to figure out the formal charges on those oxygen atoms. They don't look the same as each other, which means there's a good chance they'll have different formal charges, and that might help us figure out which one to take the electrons from, okay? If I look at the one on top, if I want to do the formal charge here, oxygen as an atom has 6 valence electrons just for oxygen atom, right? In this structure, my oxygen has 6 dots and it's got a bond, so it's got 7 electrons that I assign to it there. So it's got a formal charge of -1. The oxygen in the middle, this one, has a formal charge. 6 is the still electron count, valence electron count for an oxygen atom, a free oxygen atom. In the structure, this one has 4 dots and 2 bonds. It gets the 4 dots count as 4, the 2 bonds count as 1 each. So that's 6 minus 6. That one's got a formal charge of 0. So it's better to take an electron away from the one with a negative formal charge, because that's the one that essentially has too many electrons, has more than enough electrons already. So I'm going to take this pair of electrons from here, and I'm going to share them in there to make a double bond. Okay. If I do the same process on the nitrogen end, I'm going to get the same formal charges, right? 0 for the one in the middle, -1 in this case for the 2 of them on the end, on the top and on the right side. That means that I'm going to take a pair of electrons from one of those, okay? Let's suppose I take this one here and I toss it in there to make a double bond, okay? I also should realize that means I need resonance structures down there because when I was deciding between this one and that one, there's no basis to choose, right? So I get 2 resonance structures that have a double bond to one or the other of those. Let me see, I'm going to flip the slide here because that'll give me a version that's got everything cleaned up, I believe, okay? And so here I've got my molecule drawn out. You can see I have 2 resonance structures because on the nitrogen end here, I've got 2 places where I could put my double bond, right? My drawing program has also just taken in and sort of put some things at angles. I said I was going to talk about hybridizations and bond angles, so let's do that. The carbon down here, this carbon is steric number 4, right? Because it's attached to 4 atoms, so that means it's sp3 hybrids. That means its bond angles should all be about 109.5 degrees because that's the angle for the sp3 hybrids. Carbon atom in here is attached to 3 atoms, so it's sp2, and that means its bond angle here should be about 120 degrees, right? These atoms, the 2 oxygens in the middle, they both are attached to 2 atoms, but they also both have 2 lone pairs, which means those are sp3. That says sp3, I promise it does, which means the angles around there should be close to 109.5. They're going to be a little bit smaller than that because of lone pairs, but that's a good first guess, right? And down here, I'm back to being sp2, which means my bond angle in here, I expect to be 120 degrees. Okay, so that gives me some sense of what this molecule would look like. In this case, because my center axis of the molecule is all single bonds, that also means these pieces would all be free to twist about. So this molecule doesn't really have a rigid shape. We can say this is what the angles should be around each of those things, but the various pieces can twist and turn relative to one another as it tumbles around and finds its way. Okay, in general, molecules that have double bonds in that backbone are going to have more rigid structures because the double bond can't twist, or else it would have to break the bond. Right? If I have the bond made from that sideways overlap of orbitals, if I try and twist that bond, I'd have to break that overlap because the orbitals have to be lined up with one another to make the bond. So those are places where it can't actually rotate about.